right. Well, I guess the topic of today's lecture is Java generics. So this will be our last substantive lecture for the year. Okay, so we had this stack of int that we implemented before, and we used an array. Looked like that. So we had a stack of int. Inside the stack, there's an array of int, which is where we stored the elements of our stack. The rest of it, not so important. If you wanted to make a stack of strings, or a stack of anything else, we're kind of stuck. The only solution that we would have is to make an entirely new class. So we'd go ahead and make a stack of string, for example. And when you make the new class, if you look at the code, it's exactly the same. The only thing that changes is the name of the class, the element type of the array, the element type of push, and the return type from pop. Otherwise, the code's almost exactly identical, even if you look at the actual implementation of the methods. Right, so almost nothing changes. The only thing that changes are some types. If we go and look at the pop method, the things shown in gray, those are the only things that change compared to our int stack implementation. Right, so for a stack of string, pop now returns a string. When you go and get the element from the array in the stack, it's now a string instead of an int. Everything's the same. So it'd be nice if we didn't have to do this. So make a brand new class, manually make a brand new class, change a few things, including the name of the class, which is awkward. It would be nice if we can get the compiler to do this for us. And so that's what Java generics are for, although the compiler doesn't actually the compiler doesn't actually go in, make a new type, and change some of the types for us. The language C++, that is exactly what the compiler does. Right? It goes in, makes a brand new class, fiddles with the and then hides the name of the class so that it looks the same as the previous class. But that's not how Java works. So this is not a common problem. You make a data structure, you would like to store elements of various types. So the solution before Java generics came along was you would make a collection of big O object. And the reason this works is because everything is substitutable for object. So instead of making a stack of int, you make a stack of object. For example, using a list. Right, so here's a list that can store a bunch of object references. Everything's the same compared to our previous list-based implementation of a stack. There's literally no changes anywhere except for the element type here becomes object, the return type for pop becomes object. Oh, and I guess the list element type becomes object as well. Okay, so that actually does work. You can make a list of objects. It becomes awkward to use though. So for example, when you pop an element from the stack, you get back a reference to an object. But you probably want to reference back to the element that you put into the stack in the first place. Right, so here we have a stack of strings using our stack of object class. And we can go ahead and push some strings onto the stack and everything works just fine. When you pop an element off the stack, well, I know I pushed 3 strings, so I know I'm getting back a string. Unfortunately, the pop method returns an object. It doesn't return a string. It can't return a string. It's a stack of object. So the user of your class now has to cast the return type to the type that they want to use. Right? And so now they can use s, or the element that they pushed onto the stack, as a string. But they need the cast now, which is awkward. It's not the end of the world, though. So the thing is still usable. There's a more serious problem, though, with this particular implementation. You can make a stack that's only supposed to hold strings, but because the underlying stack is a stack of object, you can push whatever you want onto the stack. There's no way for the compiler to help you here. Right? So for example, here's my stack of strings, push some strings onto the stack. Right? I can now push the number 1 onto the stack, and this works because the compiler converts 1 to a big I integer. And now you've got an integer sitting on top of your stack. You can make another stack and push it onto your stack. And you can make a date and push it onto your stack. You can make a point, push it onto the stack, and so on and so on and so forth. right? So this list of objects, which you want to be, this stack of objects which you want to be a stack of strings, well, it really is a stack of objects. So if you have an object, you can add it to the stack. And now the problem is you have to remember what order did you push things onto the stack in, which you don't always know. And so this is the way that Python collections work. If you make a list in Python, you can add whatever you want to the list. Python programmers take advantage of this fact and use lists to store all sorts of stuff. It's awkward, right? There's no type safety here. So the fact that any element type can be pushed on the stack, it makes it impossible to write what's called a type-safe method. Right? So for example, you can write the method, it will compile, but then it will fail when you run the method. So for example, I'm going to make a list of objects. I'm going to make a stack of objects. And the intent here is that your stack only holds a bunch of ints on it, integers in it. And so this method sums the elements in the stack, and it removes the elements from the stack as it goes. Right? So it just pops the stack, sums the elements as it goes. It's easy to write. You just keep track of the sum. Right? As long as the stack is not empty, pop the stack. Right? Remember, when you pop this stack, you get back an object, so now I have to cast the object to an integer on the next line. Right? Cast the element to an integer, put it into the sum. The problem with the cast is the cast fails if elem is not an integer or an int. Even if it's a double or some other numeric type, that cast will fail in Java. So what happens? So what happens? Someone passes in a stack that doesn't have that has a bunch of ints, but there's something else, right? As soon as it sees that something else, this cast fails and the method throws an exception. And so this method would be correct if the stack had only ints on it or integers. As soon as it has anything else on it, the method throws an exception. Python programmers have to deal with this, right? In Java, we would prefer not to deal with this, right? If you want a stack of integers, it would be nice if that was a stack of integers. So the solution that the language designers came up with in version 6 of the language, I believe, 5 or 6, I don't remember which now, was this mechanism called generics. So generics in Java let you make a class, but when you make the class, you can also, you're also required to specify some extra information, namely what types are important to this particular class. Right. So the way this works in Java is you write one class. It's called a generic class. You don't have to write multiple different classes for all different types of data. Right? So I don't need to make an int stack, a string stack, a date stack, et cetera, et cetera, et cetera. Right? Instead, you write a stack class, and you require the user to specify some extra information. Right? So this funny angled bracket notation that we've been using throughout the course, it's because of the Java generics. Right? So a stack of integer is a stack of integers. Right? A stack of strings is a stack of strings, and a stack of dates is a stack of dates. The nice thing about Java generics is you only implement the stack class once, and now you get the ability to have different types in your stack for free, more or less. Furthermore, they are type safe. So if you make a stack of integer, you know for a fact, or you're guaranteed that it's a stack of integer. There's no other elements, there's no other element types on that stack. Okay, so how does this work? So you make a class, and then you put in the angled brackets after the class name. It's as easy as that. Right? So there's your class name, angled brackets, and then as many types as you need for your class, you just stick in a placeholder for those types. Right? So you don't put in the actual types when you create the class. Right? You put in placeholders. When you use the class, you substitute the actual types for the placeholders. So these names, T1, T2, so on and so on and so on, up to Tn, these are just placeholders for the types that the user will have to provide for you. So these are called the type parameters for your generic class. The parameters are allowed to be any so when the user uses your class, those have to be some non-primitive type. Right? So the limitation of Java generics is you can't make a generic type with the type int, for example. Okay, so the naming, there's no defined naming convention for the types. Right? You can use T1, T2, T3 if you like. A lot of programmers will use STU. If you're making a collection of some kind, it's common to see E for element or T just for type, plain old type. Right? If you're making something where the type has to be a number, you might see N for number. We didn't talk about maps, so key and value, not important for our purposes. All right, so I'm going to make the simplest possible generic class that I can come up with. So Java methods, they only return one value, right? In Python, you learned that a method can return a tuple of values, right? So multiple values at once, super handy in some cases. So for example, if you're writing a method that finds the minimum or maximum element in a list, it would be nice to get the minimum or maximum value and the location of the element in the list. Right? Easy to do in Python. Just make a tuple of two values and return the min or max and the location as your two values of your tuple. Right? So in Java, what you can do is you can make a little generic class that represents a pair of values. Right? You don't even need a constructor or method. Right? Just make a little generic class. It has two public fields in which you can store the min, max, and the index. Right? So you just make a class called pair. Right? It's going to be generic because I want this to work for a list of any element type. Right? So my types will be T1 and T2. S and T, U and V, doesn't matter. Right? Pick something short, just use that. And your fields are now public. Right? So T1 and T2. So first will be an element of type T1. Second will be an element of type T2. Whoever uses the pair will specify what this and this will be. Right? They can be the same thing. Right? So this could be integer, integer, double, double, string, string. They can be different. Right? That's why they have different names. And that's it, you're done. That's your class. Right? How do you use it? So here I'm going to find the maximum value in a list of integer. I should have made this something else, but anyway, it's a list of integer here. And I'm going to return the maximum value in the list and the index at which it occurs. So the maximum value will be stored in second. The index will be stored in first. Right? And so you just write your typical max method. Right? Instead of so in your typical max method, you create an int. Whoa, sorry, that represents the max value that you've seen so far. You'd create another for the index of the maximum element that you've seen so far. So here, you just make a pair of values whose types are integer and integer that are going to store the index and the maximum value for us. Right? It's just a class. So this is just an object. Its fields are public. So you can just write result.first equals 0. So the index of the maximum element I'm going to assume is 0. The value of the maximum element I'm going to assume is the first element in the list. This is safe because I know the list is not empty here. Right? If the list is empty, we throw an exception, and I can't get the first element. And now you just process the rest of the elements. Right? Every time you see a value that's greater than the maximum value, just store the information in result. Right? So update the index of the maximum value, store it in first. Update the value of the maximum value, store it in second, and now return the result. So the person who gets back the caller that gets back the result just looks at the field first to get the index, and they look at the field second to get the max. Right. So dead easy to do. You just need this extra syntax here. Hello? There is a class in here right now. Yes. Okay. It's okay. The fields are public because we're not using this class for anything except to store information in. Right? It serves no other purpose. So we can safely make these fields public. T1 and T2, remember these are the placeholders for the types that first and second will hold. Okay, so how do you make a generic stack? Well, it's pretty straightforward, right? It's going to get a little bit complicated because we're using an array. So if I want to turn our array-based stack into a generic class, right, simply add in our extra generic type parameter here. Right? So this is going to be a stack of some element of type E. Right? Everywhere where we wrote int before for the element type, you're now going to write E. Right? So instead of an array of int, we have an array of type E. So there's our field for now. Okay, so in our constructor, we need to make an array of type E. Right? So we need somewhere to store the elements, so I have to make a new array. Right? So if in Eclipse you write new generic type here, some number here, Eclipse will complain. Right? It'll say you're not allowed to make a generic array. Right? So you can't make an array of an unspecified type here. Right? Okay, so that line on the previous slide causes a compilation error because in Java you're not allowed to make a generic array. Right? The solution in Java is to make an array of object instead. So we got to go back here and change E to big O object. I'll explain why you can't make a generic array shortly. Boom, boom. Okay, so go back into your class, change the generic array type to a type, so that the array is of type object. Right. Now in your constructor, you can make an array of object. Java's perfectly happy with that. Oh, sorry. All right, so why the heck doesn't this work? So it doesn't work because the first version of the Java language had arrays. They didn't add generics until the fifth or sixth version of the language. And so by that time, it was impossible to adjust the ways that arrays behave. It would affect too much existing code. So arrays are funny in Java. The way that they behave with inheritance is odd. Okay, so if you have a type called sub, and it's a subtype of super, then arrays are very strange. Right? So if we have an array of type object, right, and we have an array of type string, string is a subclass of object. So as far as Java is concerned, an array of string is a subclass of an array of object. Right? So an array of string inherits from or extends array of object. Okay, so what does that mean? So if I have an array of object, objs, right, can I store an array of integer in objs? Right? So the answer is yes. Right? As far as the language is concerned, an array of integer is an array of object. Right? So we can store a reference to an array of integer in objs. So the answer here is yes. Okay, now, remember what objs is? It's an array of object, right? So the first element of the array is a big O object. What can you store in a big O object? You can store anything in a big O object, right? So I can store the string hello in the first element of objs. Right? As far as the compiler is concerned, this is perfectly fine, right? A string is an object, therefore I can store hello in the first element of this array. Notice though that the actual array is not an array of objects, right? It's actually an array of integer. So does it run? The answer is no, it doesn't run, right? As soon as you try to run this program, it barfs, right? Because you're trying to store a string in an integer, right? And so the compiler doesn't detect this. The compiler thinks this code is correct, right? When you run the program, your Java virtual machine knows that this code is in fact incorrect, and it's the virtual machine that complains. Right, so this compiles but does not run cleanly. You had a question? Hello? Front row? Hello? Never mind. Carry on. Okay, so generics are said to be, sorry. Oh, right. So the way that arrays behave in inheritance, arrays are said to be covariant. Right? The relationship here is really between string and object. Right? If you have arrays, then arrays also behave in the exact same way, right? They behave the same as their element types. So that's what covariant means in this case. When the creators of the language created generics, they decided that generics shall be invariant, right? So if you have a list of object and you have a list of string, there's no relationship between these two types at all. Right? There's no association, there's no dependency, there's nothing, right? There's no relationship between these two types. So a list of string is not a list of object, right? A list of object is a list of object, a list of string is a list of string, a list of integer is a list of integer, right? So for any two distinct types, T1 and T2, right, there's no relationship between a list of type T1 and a type of list T2. So if you make a list of big O object, right, can I store an array list of type integer in OBJS, right? And so the answer is no, you cannot, right? This is a list of integer, this is a list of object, right? There's no relationship between these two things. I cannot store that list in this reference here, right? So that doesn't work. But it does work if that's an array and that's an array instead, right? So, so that's why Java will not let you make an array of generic type, right? It's to try to minimize this from happening. Okay, so once you've got your array of object inside your generic class, the rest of your changes are very small. So here's push. Everything's exactly the same, right? Except for that line right there. This used to be an array of int. It's now an array of object, right? Nothing else changes. Pop. This used to be int element, right? We used to go into the array, grab the int from the array. Now it becomes our generic type, right? So our array is storing our array is an array of object. We're going to store elements of type E in the array. The only complication here is that you have to cast the result, the element that you're getting out of the array to type E here. The cast is required because that element, its type is actually object. You know from push though, right? Push always takes in an object whose type is E, right? So you know for a fact that the array has only elements of type E. So you also know that this cast is safe, right? You wouldn't know this if you somehow leaked a reference to the array, right? So that's the danger here. If you leak a reference to that array right there, anybody can put whatever they want into that array because it's an array of object. So the array stack is trying to be a composition of an array. If you leak the array, your generic class is going to break. Right? When you try to do that cast here, if someone has managed to insert a different element type into your array, that cast will fail at runtime. So make sure you don't leak the array if you implement one of these types. Everything else is the same, so that's the only thing that changes. Right? So the number of changes to make this into a generic class, very small. Right? One line in pop, one line in push. One field changes, and you have to add the generic type parameter to the name of the class. Right? 4 lines of code, 4 very small changes. You now have a completely generic stack. Right? You can make an array stack of whatever you want now, and the class works exactly the way you want it to. So when the designers of the language created generic types, one of the goals was to make it as easy to use, as easy to do as possible. And it is easy to do once you wrap your head around the fact that instead of using an actual type name, you use a generic type name E, or T, or whatever else you want. Okay, so we've got a generic, we have a generic array-based stack. We might as well go ahead and change our interface now to a generic interface as well, which is even easier to do than changing the class. Right? So our interface stack used to look like this, right? Yes, it used to be a stack of string, right? So push would take a string as its input, pop would return a string, right? Turn it into a generic interface, that's it, right? Add the generic type parameter after the interface name. Change the element type for push to E, and change the return type for pop to E as well. Right? And you've now got a generic interface. Okay, finally, we're going to change our array stack class to say that it implements the generic interface. But that's easy to do too, right? Our array stack of type E implements our stack interface of type E. And away you go, and that's it. You're done converting our array-based stack into a fully generic type, right? Okay, any questions about generics or converting a class into a generic class? Yes? Yeah, absolutely. And it's dead easy to do too, right? Hang on, I can, if you want to wait a minute, I can pull it up. I just have to start up Eclipse and I can show you exactly what it looks like. I didn't hit cancel, did I? Oh, is that it? No. Oh, fine. There we go. Anyway, there we go. Okay. 124. So under, if you downloaded the source code, it's sitting right in generic basics linked stack. Let's maximize that. Okay, there we go. So your linked stack, you add in the generic type parameter, right? We have a generic interface now, so you also say it implements a generic stack. The node class now becomes generic as well because the node is what's storing the elements, right? So the node also becomes generic. Your top node is now a node of type E, right? Your element changes its type to E, right? The next node in the sequence becomes node E. Basically, anywhere there's node, it becomes node E, right? And anywhere there's an element, it becomes E instead of the int or whatever we had before. Yeah, replacing the type of the original element that we used, right? So if we had I don't remember, I think it was a linked stack of int, right? So anywhere where there was an element of type int, you just change it to type E. Right? That's it. Like it's dead easy to do. So push, it's the same change as before, as for our array-based stack, right? Instead of having an int as its input or a string, I guess it was a string before, right? Before we'd make a node and we'd say new node and this would be a string. Now it's node E, that's now an element of type E, right? Nothing else changes here. It's even easier to change this than the array-based one. For pop, you're going to return an element of type E, right? You don't need the cast or anything special here, right? Your node is already generic, so you just get the element from the node and away you go. Right? Oh, but toString always returns a string, right? So you can't change that. Right, toString always changes the string, so you don't want to change that, right? You're not going to change every occurrence of the type, right? You have to, it's where when you're using an element, you change the element type. Yeah. So converting an existing type to a generic type is normally very easy to do. Generic queues, I guess we'll look at this. Do I want to look at this? Yeah, let's look at this. Yeah, I don't have. That's right. Yeah, if we didn't have generics, well, at the beginning of the lecture, I explained what happens if you didn't have generics. You're either stuck duplicating the class over and over and over again for your other types, or you make a list or a stack of big O object, and you're stuck having to deal with the fact that whenever you pop something out of the stack, you get back an object instead of the type that you want.
What is the parameters for object you created?
Sorry? Are some type that you made? Yeah, of course. Yeah, types, classes are user-defined types. So if you make a type, you can pass it. You can use that as a generic type parameter. Yep, absolutely. I guess we'll do this. Generic queues. So this is a new type of data structure, but it's very similar to a stack. So a stack of stuff. A queue is, well, it's a queue of stuff, right? It's like a line of people waiting for a cashier or something, right, to get into a concert or something like that. So in a stack, there's the notion of the top of the stack. In a queue, there's a front of the queue and there's a back of the queue, right? If people are polite, they always enter at the back, right? That's the idea. There's something called a priority queue, where you can enter wherever you want based on a priority. But that's much more complicated to implement. You'll learn about those in SYS 235. All right, so queues are the other simple linear data structure in computing science. They only support two operations, sort of like a stack, right? NQ adds to the back of the queue, and DQ removes the element from the front of the queue, right? So remember, on a stack, it's push and pop, right? Everything happens at the top. In a queue, it's NQ and DQ. Something happens at the back, something happens at the front. Right? If you wanted to, for an actual queue implementation, you would add some extra methods, right? How many elements are in the queue? Is the queue empty? It's often useful to look at the first element in the queue but not take it out. Right? You might want to search a queue for a particular value. Okay, so what does enqueuing look like? So when you implement the queue, you basically need to keep track of where the front and back elements are, or at least, or what they are. Right? So if you enqueue an element into an empty queue, right, the front and the back, they both point at, or they both are the first element in the queue. Right? So enqueue a second element, so it joins at the end of the sequence. Right? So the B shows up at the end, so of course the back of the queue now changes. Right? Enqueue another element, right? So now the back changes again. Notice the front doesn't change when you enqueue. Right? D and then E. Right? When you dequeue, stuff's going to come out at the front. Right? So when we dequeue, the A comes out. So S is going to be equal to the A. It's going to pop out, and conceptually, everything moves forward in the sequence. Right? So this is the way it would work in a physical queue. Well, this is the way it works in most physical queues. Right? Take out the B. Right? Everybody moves forward. Right? Take out the C. Oh, everybody moves forward. Right? Okay, so if this was an array, right, and you implemented it this way, right? So the A comes, oh, sorry, I'm going too fast. And the A comes out, right? Notice what you have to do. You have to shuffle all the elements forward one position in the array. Right? If your queue has n elements in it, you have to move n minus 1 elements forward in the array. Right? So the naive way of implementing a queue, where you put the first element of the queue at the front of the array, and the last element of the queue somewhere in the middle of the array, right, or towards the end of the array, right, is inefficient. Right? Shuffling all the elements forward every time you dequeue is O(n). Okay, eventually you get to the end of the queue and everything disappears. Right? So remember, in a queue, when you dequeue, everything happens at the front. Right? So it's the front element that's going to change after I dequeue this element. Right? When you dequeue the last element, though, the back element also changes. Right? There is no back element anymore. Similarly, when you enqueue, everything happens at the back of the queue except when you enqueue an empty queue. Right? When you enqueue into an empty queue, the front also changes. So you have to keep those two facts in mind. Okay, queue is what's called a first in, first out data structure. A stack is a first in, last out data structure, right? So in a queue, the first element in queued is the first element out. In a stack, the first element you push onto the stack is the last one out. Just like stacks, queues are widely used in computer science, right? So any large web server is going to have a queue in it, right? Amazon, there's probably millions of concurrent users for Amazon at any one time. They have many, many servers, right? Each web server keeps a queue of requests, right? Every time you click on a link, that request goes into a queue somewhere on Amazon's web server, right? Eventually, your click gets served by the web server. Right? Operating systems use queues to distribute resources, right? So there's a printer queue. If you ever printed stuff in an office where there's lots and lots of people using the printer, right? You'll know that your job goes into a queue somewhere, right? There might be 10 people who have printed something ahead of you. Your job goes in at the end. Eventually, it comes out at the front. Right? Network devices use queues to determine which packets to service. So some information that travels over your network is more important than other information. Typically, your router will do some processing of the packets that arrive on it to determine which ones it should deal with first. Classic search algorithm in computer science is called breadth first search. You'll learn all about this if you continue in computing science. One way to implement it is to use a queue. All right, there's an entire theory, mathematical branch of theory called queuing theory. I believe there's a fourth-year math course about this. And for sure, there'll be a course in electrical engineering on this. Okay, instead of implementing a queue of int or in a queue of string and stuff like that, we might as well just jump right in and make it a generic queue. So our queue interface has the following methods in it. So there's a size, there's isEmpty, right? There's enqueue, there's dequeue, there's front and back. So front and back let you look at the front element and the back element without taking them out of the queue. Enqueue takes an element, adds it to the queue, and dequeue removes the first element from the queue, returning the element back to the caller. Okay, so implementing a queue with a list is dead easy. So it's exactly the same as a stack, except dequeue removes the element at the front of the list. Right. So our list-based queue implements our queue interface. Internally, it has a list of elements type E. Right. You could make this array list. I just made it list. Right. Our constructor makes a new array list and stores that in queue. Right. Size is easy. It's just the size of the list. Right, enqueue, you just add to the end of the list. Right? So this.queue.add. Dequeue, you remove the first element from the list. Right? So if the list is, if the if the queue is empty, we're going to throw an exception. Otherwise, remove the first element from the list. And here you see we're stuck. If we're using an array-based list, this is O(n) in complexity. Right? To remove the element from an array-based list, to remove the first element from an array-based list, you have to shuffle all of the remaining elements forward in the array. Front and back, that's, the reason I created this throw if empty method is because I need to use it 3 times. Once for dequeue, can't dequeue an empty queue. You can't look at the front element of an empty queue. You can't look at the back element of an empty queue. Right. To look at the front element, you just get the first element from the list. To look at the back element, you just get the last element from the list. Right. 2 strings, dead easy, right? You just ask the list for its string representation, and you've got a functional 2-string method. Equals is dead easy, right? You ask the list to compare itself to the list of the other queue, right? Because list also has an equals method. Okay, if you want to do this with an array, and I'm not sure we're going to get done, it becomes slightly trickier because you want to avoid this O(n) price of moving elements forward in the array. Right? To implement this using an array in a slightly more sophisticated way than just shuffling everything forward, we're going to need 4 fields. So we need an array of elements to store the queue, to store the elements of the queue. We're going to want the index of the front element. We're going to want to keep track of the index of the back element. Remember, in the stack, we simply kept track of the index of the top element. We also need to know how many elements are actually in the queue, right? We know how many elements are in the array, right? Or we know the size of the array, but we know the length of the array, but the size of the queue is the number of elements in the queue, right? Which is different than the length of the array. Okay, so here's our array of elements. Right, now, it's a generic array, so that means it's, the array has some reference type. Sorry, it's an array of object, so it has some reference. So in the array are a bunch of null values here. Front is going to be the index. So I think, what's this previous slide? Okay, so this says it's the array index of the element currently at the front of the queue, but we're actually going to do something slightly different. It's going to be where the first element would appear if there was something in the queue. Right? So the first element would be at index 0 if there's something in the queue, but there isn't. Right? The back element we're going to set to -1 for the time being. Right? So the back element looks like it's always going to be, the back element we're just going to set to -1 for now. Right? Okay, so to enqueue an element is exactly the same as pushing an element onto a stack. If you have to, right, if you're out of room in the array, you have to copy the array, make a bigger array, copy the array into the new array. Right? Otherwise, if there is room in the array, you just move back one position to the right, and you set the element at array back to the enqueued element. Right? So remember, in a queue, everything happens at the back of the queue. So to enqueue, when we enqueue an element into this queue, right, back, we add 1 to it, so now its value is 0. Right, insert the element at index 0. Right, insert a B, so add 1 to back. Right, insert the element at the back index, and so on until we have 5 elements in the queue. Right, so to enqueue, add 1 to back, set the element at back. To dequeue, right, we know where the front element is. Right, where front points at the first element, or it's the index of the first element. So we're going to remember what is the element. Right? Unlike for pop, where we didn't bother setting the value in the array, here it's important that you set the element to null, and I'll explain why shortly. You then move front 1 position to the right and return the element. Right? So to dequeue the A out of the queue, right, we're going to remember A was sitting in the first element, so elam will be A. I'm going to set the element in the array at the old front index to null, and then I'm going to move front 1 position to the right. Right? So we've got the A somewhere. We've remembered what it is up here somewhere. Front used to point to the 0, so we're going to set that element to null. Right? And then I'm going to move front 1 position to the right, so it's now equal to 1. Okay, so the reason why we set this to null is because this is now an object reference sitting in the array. Right? If we don't remove the reference from the array, then the object that is being referred to can't be removed from memory. Right? So the rule in Java is if something has a reference to an object, that object will not be removed from memory. So if we leave the reference sitting in the array, and we never do anything with this array again, so in other words, the queue lives for the rest of the program, but you never actually use that element again, the object that was referred to never gets cleaned up from memory, which is, if the queue ends up being very long, you're going to have a whole bunch of references to objects that are no longer being used, and there's a chance that you run out of memory in your program. Or you end up, at the very least, you end up consuming much more memory than you need. Right? So it's important that when you're done with a reference when you're done with a reference that might live for a long time, you should always null out the reference. Okay, so dequeue another element. Oh, sorry. Right? So to dequeue the B, we're going to remember what the B is. We're going to move front 1 to the right. We're going to delete the B from the, we're going to set the element at index 1 to null, like that. Right? Dequeue again. So remember what the C is. Set this to null. Move front 1 to the right. Right? Dequeue again. So there's one element in the queue, right? Front and back are both pointing at the E, or they're both index 4. If you dequeue again, right, set that to null, right, move front 1 to the right, right? And now we're back in the situation where back is in front of front, right? So back is now 1 less than front in an empty queue, just like it was at the beginning. If you try to use this as your indication that the queue is empty, it won't work, right? And you'll see why shortly. Okay, in queue again, and then in queue again until we hit the end of the array. All right, so when we hit the end of the array, the queue is not full, right? There's still 5 more positions that we can use in this array. And so when you implement the queue this way, you have to deal with the fact that your index might have to wrap around to the other end of the array. Right? So if I enqueue another element, what I would like to be able to do is to wrap around to the front of the array. Right? Back now points at index 0, so it's less than front, right? So that I can use the remaining space in the array. Right? And if you keep on enqueuing, now the queue is full, right? Every array location is occupied. Back is exactly 1 position behind front, which is exactly the situation when the queue is also empty. So when back is 1 less than front, the queue is either empty or it's full, but you don't really know which. Okay, so if you dequeue, the exact same thing is going to happen to front. Right? So we start to take elements out, so front marches to the right. Right? When you take the element out that's sitting at the end of the array, front is going to wrap around back to the front of the array. Right? Okay, so you can imagine that this array looks like this. Right? So this is what we want to do in code. We want this to be a circular array of values. Right? This picture here, exactly this picture here. Right? Q's at the front, right there. U is at the back, right? As you enqueue elements, back rotates clockwise, right? As you dequeue elements, front rotates clockwise, right? When back reaches front, or when back reaches the position in front of front, you know that the queue is full or empty, right? Because front can catch up to back and end up being pointing at the next element here in an empty queue. Right? So your front and back your front and back indexes, you can imagine them as rotating clockwise. All right, so what does this look like in code? So it looks a lot like a stack, right? There's your array of objects to hold the elements. There's front and back, and there's size. Right? What does your constructor look like? Well, your constructor just has to set front, back, and size, right? Oh, and of course, make a new array. So front is 0, back is -1. It doesn't actually matter what these values are, as long as back is 1 less than 0. I suppose front could be the last element, could be the index of the last element, and back could be 0 as well. That would also be possible. The queue will still work even if you implement it that way. Right? This is probably the most natural way of doing it. Can you copy another array queue? The answer is yes, you can copy another array queue. Right? How do you copy another array queue? Well, you just copy the other queue's array. Right? How do you copy the other queue's array? Just use array's copy of. Right? So when you copy the other array, make sure you copy the other array, including its length. Right? Don't make it bigger, don't make it smaller. Right? Copy its length. That way you don't have to worry about front, back, and size. Right? You just copy the other's front, back, and size. If you make this a different length, you'll see shortly that you setting these like this will not work correctly. Front is easy. You just return the element at the front of the array, right? Casting the element to type E, because remember, this is an array of object, and the caller wants back an element of type E. Back is exactly the same thing, right? Return the element at the back of the queue, right? Casting the value to type E. Dequeue is also easy, right? There's nothing that we have to worry about in dequeue, except for the fact that front can wrap around at the end of the array. But that's easy to deal with. Right? So remember what the element is at the current front of the queue, right? Null out the value at the current front of the queue, right? Now move front 1 to the right, right? If it falls off the end of the array, you want it to come around back to the front, right? And so the easiest way to do this is to add 1 to front, right? And then to deal with the wrapping around, compute the, take this value, divide it by the length, and compute its remainder, right? So here, so if front is here, so it's a bit 15, right? I'm going to add 1 to it, so it becomes 16, right? The length of this array is 16, right? So 16 divided by 16 is 1 with a remainder of 0. So the remainder of 0 sets our value for the new front index, right, which is down here. Okay. So there's where the remainder operator, this is one of the situations where the remainder operator is very commonly used in programming, right? When you need to wrap a value back around to 0, divide by the number of things that you have, and that typically does what you want it to do. So instead of setting this front to this front plus 1, set it to this front plus 1, and then take the remainder after dividing by the length of the array. Don't forget to adjust the size of the queue, right? You just took something out, the size decreases by 1. Okay, what about NQ? So NQ has to deal with the fact that we have to resize the array. It's slightly more complicated than when we had a stack. Oh wait, we're out of time. Okay, we're out of time, so I'm going to stop there. And I will finish this up in the next lecture. And then I'll also return your quiz 2, and I'll talk about the exam on Monday. Right? And that'll be the end of this course. Right, so see you next week.